Very excited to hear from Yanky Hoffman, who wanted to only be introduced as a fellow Slacker.
Very good. Thank you for the introduction. And as I said, I like sharing back. We have a nice community here. So I thought I have a way of, I'll try, help other people. There's a OOP, object-oriented programming is a hard thing for plenty of newcomers. So there's a way, finally, once I got some sort of a knack on understanding it, I thought I'll share the path of simplifying it, what this keyword, self in Python, methods, properties, all those stuff. So David, I can't share my screen, so if there's something on that. Perfect. Okay, so just to simplify mine, if I'm speaking too quick, anyone just so say anything, I'll try to fix it up. So I'm going to implement the generic stack as in, you push on top and you pop it off, a LIFO last in, first out. And we'll start with regular imperative programming, as in we'll just start with functions and stuff, and then we'll slowly turn it into an object. So in order for the stack, the way we're going to build a stack is going to be fixed length, as in we could have like n number of elements, but not just once it's full, it's full. We're going to have the last n elements are going to stay in the stack, the rest are going to be forgotten. So the way we're going to do it is we're going to create a list or an array, and we'll keep the last 15 elements running round robin and removing the first ones added. So for that, we're going to need a stack, which is going to be an empty list of, let's say, 15 elements. To make it even better, we'll make max elements plus 15. So we'll have a count where to go back. Max elements, so we have a stack. We'll need to remember where our next index is going to be, where the next place to add an element. In a second, everything will make sense, hopefully. And the current size, just if you want introspection, where we're up to. Each element, when we're going to add an element, we'll go to stack next index equals element whatever we want to add to it. And then we'll increment next index. Oopsie. Plus equals 1. So just to use this in regular code, it's not going to, have it each time we need to add to the index, to the stack, and continue on is going to be, repetitive. So we create a function for that. So we'll call this stack push. And then just one little thing we'll need to check. Remember, after each time we increment the next index, if the next index is equal to max elements, then we'll need to have next index equals 0, as in to go round robin and go back to the start to the first element on the first slot in the array, and then size equals, and also we don't want to have, since the size is going to be maxed on the max elements, as in we're never going to have more than how much elements we allow. We're going to use a max function over here. We're going to get size plus 1, or max elements, not max, we'll need a min. Which one of those two is smaller? That's how the size is always going to be. So we'll always have count on the size and up to max elements. But if we know this, this is going to fail, since we're in the function next index is declared over on top. And it's not in this current scope, it's in the global scope. So we'll need to say global next index and global size. Then we'll have another function, stack pop. And this is just going to go to next index and it's equals 1. Since we set the next index available for the next push, But if we want to pop, we have to go one behind. And once again, we'll have to check the same thing. If next index equals -1, and we know where we were up to 1 minus the max elements. And then equals stack index, and we'll have stack next index back to none for garbage collection, that we don't keep the slot, you know, just dangling references to whatever we want to put onto the stack. And once again, we have to remember to go to global index and global size, speaking of which, we need to remember to have size minus equals 1, and we need to return the element that we popped off in this line. Now, one little thing is, if we're constantly just going to go backwards and backwards, we're going to end up just returning null, all those nuns. So we could make a new little function, and if stack is empty, and we're going to return size equals 0. So if you know size equals 0, then there's nothing to push off to pop over the stack again. And just for the sake of clarity, we'll have a little our custom exception for this. Exception pass. And this is how we inherit from global exception. We'll check if stack is empty, and then we raise stack empty exception. So that's the start. Now, if we will look at it, we know that we're modifying global state. And the point being is, so let's say if I want to take this whole code and put it into a library function, let's say I want to create my little stack library and import it. So let's do Control-C, in the file, stack.py. And we have to go from, it's not a from, let's go import stack. And over here we'll do def main. This is our main function going to be, and we'll have where stack push 1. Whatever the case is going to be, is as soon as we try running this a second time in the same thread or the same point of process, and we're not going to start with an empty stack. So let's say if we want to do assert stack is empty, and we'll run this piece of code twice. Main and main. We are going to fail this on the second run, as the stack is not going to be empty since we pushed on to global state and we never cleared it, or we don't have a way to get a new instance for each one. So a simple solution might be is that we'll start keeping track of those 3 variables on our own and passing them in. But the point of having a library as opposed to client code, as in my main.py file, as opposed to stack.py, is the idea that I get an API. I imported stack. I know stack is empty. Stack push. Those are the functions which I need to. I have a signature. If I give it an element, it'll push it onto the stack. If I pop, I get something over that stack. Stack is empty. I don't need to worry about the internals, like it has a size, it has a next index. So the idea, what we could do is, first of all, we'll have a black box. Let's, just for readability's sake, because all of those functions, since we're namespaced already under stack.py, we could rename those functions regular plain as a verb. And over here we'll have stack that is empty. Same here for stack that push. And now for our sake over here, oh, then save it. Maybe it has that function. Now those three variables which are relevant for the iteration is we could combine them together in a list, which is an array. But Python, you could have multiple types, since everything is just a Python object. And the first one will have our thing none times max elements. The next thing will be next index of 0, and the next thing will be size of 0. And we'll need to keep track on our own, know which element is at which point. So we could have, once again, global pointers. Let's say stack is equal 0, and next index is equals 0, of stack is equals to 0. Yeah, the 0th element. Next index is the first element, and size is the second element. And then in each each one, when we want to go to the list and get whichever element at that point, we'll just pass the globals which we defined up here. And once we have that already, we know that we have much a better way if we just create a dictionary, and we'll have key access into it. And this will be the stack. This will be the next index, and this will be the size. So now we have named the access, and going to that point. So we'll have to accept the stack in each one. I'm sorry if I'm going too quick. And we'll accept the stack, and that stack will just go to sorry, not that stack stack next index is equals to lem. If you get what I'm doing. If we're going to pass this object, which we're going to call stack for now, we'll worry about it in a minute. So we have stack. So in stack, we'll go to the stack, which is this part of the dictionary, and we'll go to get the stack, whatever is at stack next index, and that will be the element we're pushing onto it. Once again, stack next index plus equals 1. Once we add that, we know we need to do it for each of these. Stack. It's empty. This is empty as the function down here, which we'll know. And once again, we'll have the same here. Same. Sorry if there's too much stack around the point here. I forgot to pass stack for each of those. And for this empty, we'll have to pass that stack further from top into this empty function. Stack will be passed here, and it'll return if that underlying stack size is 0. And now for our sake, we'll create a new function here, def new, which will take nothing, and it will just return our new instance of stack. Oopsie. And the point being is the way we'll use it in code is first thing we'll need to remember to create our own stack. Stack.new. And this shouldn't be just the deal, let's just call it S, as we're going to shadow the namespace up there. Stack.new. And then I'll have, this is a black box. I don't need to care how this is implemented. I'll just pass wherever I call stack, any function on the stack method, I'll just pass along S to the stack. So point being, so let's go back. So we get a black box of the object. We could get as many instances of that object that we want. And then we have our namespace, which contains all the methods that is related to the API we exposed. And we just pass as the first element, being that we decided on that, the instance we created, and then we could just run on that object. So point being is we need to keep two pieces of information. We need to keep both the instance and both the namespace where we're tied on those methods. If I could, like, perhaps we could do, since knowing in Python, we could have functions or top level objects, we could pass them, we could store them anywhere. Maybe if I want to do like push, and I'll put the push function here. The issue being, but I'll need to, even though this will work, let's say I'll be able to go here, s push, oops. I'll still need to remember to pass s once again in there. So this is where classes, and that's the entire idea of object-oriented programming is, it just, these sugars for syntactic sugar, as in since we have an s, which we create by calling a function which is called stack.new, and we pass it to the namespace. All the methods in that namespace is what we do with class is there's two parts to the class. First thing is we could have the object, as in class is a container. Let's say each instance which gets created, not the correct words. Each instance that we create, we could assign data onto that instance. As now we're using over here a dictionary. The class has its own way of storing data. And then there is the namespace of the class on which we could create methods, which gets bound on its own into by using that's what code does. So let's just try to simplify it a bit. So class stack. Now first we'll start with a push. Ints I'm calling is the instance we're going to pass. Just as in this function over here, we're using the same exact signature stack. Instead of calling it stack, since we have multiple stacks, we're calling ints as in for instance that we're going to create, and an lm. And we already know that we're going to go to ints stack, but reality speaking is part of the class signature is it helps us, it gives us access, data access, so we could get IntelliSense, all the IDEs could help us code it out, and I mean, a lot of better features. So go stack is ints that next index equals lm. The issue we have now is we never yet defined that ints contains a stack, ints contains the next index. Just to make it, before I'll explain even more, we'll just do it this way. We'll have stack equals to, oopsie, none times next elements. We'll have next index equals 0, size equals 0, and then we'll just be able to take all those functions reality. Oopsie. X. Okay. Instead of ints, I'll just call stack, we'll call them ints. Let's do a little rewrite, sorry, ints, that stack, ints, that next index equals lm, ints, that index equals 1. Just keeping the old code for reference, if ints that next index ints ints that size equals to the min ints 1 and max elements. So that's for this method. Pop ints, we'll check ints that is empty. Oh, and that's the beauty of classes. That's what we'll be able to see right over here is the namespace just resolves this way. That if we go, we can call both. We can call s equals stack, and then we'll go to oopsie, stack that push. We pass along the instance we created. Say s is equals to stack. Now, for now, let's imagine we'll have a stack.new, which will return, which will create us our s with those three properties, all those fields on it, as in the stack, the next thing is the size. And I will call the namespace again, stack.push, and for the first thing we'll pass in an S, and the next thing we'll pass in whatever we want to push onto the stack. The idea of all those programming languages is that you could do s.push element, and this just translates back to this line of code. It finds what is the namespace of S. Does that contain a method called push? And if it does, it just passes this back to the namespace push as the first element. It adds it on element 0 of the function call, as in over here I'm only passing one element. It's pushing that one element before all the other pushed elements. Oopsie. So let's just index. Stack. Means that size. Let's take an int. As we see, is empty takes an ints, and it just, and I call it, passing it nothing, and it just passes to that. The reason I'm getting this is undefined. Oh, I didn't define it. This is my linter saying that should be named as self. So that's just convention, as in, since see, it's going to work if I put an ints, as in that's the element I'm passing. Convention is in Python to use self, and that's you get all those color highlighting. Now, for the idea of a constructor is in Python we do .NET self, and in that you could pass whatever elements you want. Now, most other programming languages which are compiled, let's say like C# or all those programs or those languages, they create data onto the stack or onto the heap, wherever it is, but it gets created in a chunk. It's not a dynamic language that you could just tack on pieces of code or pieces of data one onto the other. Python is just, when you create a class, you get a dictionary, and just like you create a dictionary, and then you could go to the dictionary, let's say D is equal to dictionary, and you go D A is equals 1. This is dynamically later, this dictionary grew. So in Python, the same idea is the class, the self which we pass in, which is the first instance we get, is just a dictionary. And we could just tack onto that all those, all those elements over here that we request, that we wanted. That's how we automatically get access to all those stuff. Init, those are Python magic methods called, those that have the double underscore on the sides, which the idea of those is they hook onto the language and also into like I said, syntactic sugar. So if I say import stack, s equals stack dot stack, and then I say s dot push 1 is the same as stack dot push s and 1, the idea being when you make stack with the parentheses, this automatically calls stack under init, and it passes the first element. It just creates a in init. It just gets it ready from different functions. It's not we never need to pass explicitly the self keyword anywhere in Python, and neither in any other languages. The idea of Python is on a belief of explicit is better than implicit, that the self keyword needs to be declared and called on this method. If we would go with compiled languages, let's create ourselves a new class over here, stack. Those languages, when you want to create a new stack, the way we would do it is we do var s equals new stack. The idea of the new keyword here is we need to create place in memory for the object that we're going to declare over here. Now, C#, Java, all those languages, they know that when you say int var I equals 42, it knows what data type this is and how much storage such a data type needs on the stack or on the heap. So it could automatically create place for this on for in memory. When you want a stack, we need to declare what this thing is going to contain. So we'll need to have not var. Sorry, here we go private. Private also thing stack, and we'll go private int next index. I'm not doing it fully correct here, but the idea being is when you call new stack, it finds whatever method, whatever properties are defined on the class, and it creates a data structure containing place for both the stack and for the next index, and it's going to know on its own that when you call public push, and I'll just have it work. You're going to call the stack, it's going to know implicitly that the stack is what we wanted over here. So int stack. When we call push, there's an implicit this keyword passed over here, which is an instance of the type that we are creating. But we never, in all those languages, we don't declare, we don't write it. The way the point where we do use it is, let's say if we have an element over here, which we'll call lm as well, and you want to be disambiguous on what lm we're talking. In such a case, we'll go to explicit to this that lm equals lm that we passed to be able to differentiate which lm is the outer one and which lm is a new local variable here and what's on the class. Oops. So that's the difference between the compiled languages and dynamic languages like Python. And David, still have time or? Continue. Something else. All right, perfect. So now a little point. So that this is on what the difference between object-oriented programming and imperative programming, as in saying s equals a new stack and then pushing on using a function which takes the object that we're going to modify as immutable objects, which is going to modify in place. Next thing is something which you'll find a lot on compiled languages is private, public, all of those accessors. Those stuff are not for like security, as in, let's say I want to store passwords on something, I'll say private string password that no one should be able to access. That's not the point of the private and public. The idea of private and public is this next index is purely internal. For the API needs to write one thing. It could take an element and push it on top of the end of the stack, and it could pop off the next element. There is no need for the user to be able to modify or even know where that element is going to be. All they need to know is there is a max element, how big the stack could be, and this is going to get pushed on the top of that stack, and the next element and the next element. This is not, there's no need to display this to the user. And what's even more is if the user could have an access point to this and to modify this in place, the entire code could break. If the user at some point in code over here will go, here's that next index equals to 25, we're going to get an index error since we're off the stack. Or if he's going to move it somewhere else, we're not going to have the entire point of the stack being last in, first out. We're not going to have it. So for that idea, there's the keyword private, which says no one outside of the namespace in this class could access it. And in Python, we use a convention. We just add an underscore before the words that we don't want to expose. That it's a convention, like you should know the developer who wrote this code. This is code which changes internally in the class. This should not be modified outside of the class. The next thing which we have is a property. In compiled languages, we might have such stuff like getters and setters, it's called, which is also just syntax sugar. So let's say if I want the user to be able to see the size at any point in time, just like we have the is empty, perhaps I want to give them a nicer way just to see the current size. We could do def get size, being that size is a private a private variable, we will need to, we would rather have a getter function for them open. And we'll go return self.size. But the way that the user will have to call this will at each point be s.getSize, which is not, the most nicest way to see. So there's such a thing which is called a property. I just call the function however I want and returns the size. And the way you get it, there's that size, and that just evaluates back the size the way it should call a function and get the internal value of this. Another point which just might be useful is, let's say if I want, in this case of a stack, we have nothing which we could set from the outside. But let's say if I want to have some sort of a function which will only allow a class which only allows positive integers or any number only positive to be set, we'll have let's say size setter. Size value is the value which will be passed, and we'll go self.size equals value, and we could just add some checking over here if value is greater than 0, so to make sure that it's positive, etc. And the way this will be is you go self.size equals 42, and this just evaluates the self over there, and value is whatever is on the right hand side of the caller. Oops. So it won't be this again. Okay, I think for now that'll be it.
Hey, open up for questions?
Yeah, sure.
We're open for questions. I think anyone can unmute themselves.
I'll throw one out there. First of all, great presentation. Thank you.
Thanks.
What's your opinion on using Python for object-oriented programming as opposed to languages where it seems more native?
My opinion is that I started programming with Python, and I just love the language. It's so quick and everything. Mine's quick to develop and to prototype in it. And object-oriented programming, it's a beautiful paradigm. And when you're coming from imperative and you start learning object-oriented programming, it could be that functional is better. But object-oriented programming is really a super simple thing, and it's very nice. And I use all my programming is in OOP currently.
What about using something like C++, where a lot of these concepts are more enforced, where you could have, or C# even, where you can have like private member variables and stuff like that?
Once again, private and public. In Python, we have this belief which is called we're all consenting adults here, that if I put an underscore under it, this should not be modified by client code. If you're going to modify it, you're not going to be secure that this framework is going to work, whatever piece of code you installed and you hope to work with it. If you're going to change the signature, it's not going to work. Just to like understand, if a signature in C++ calls for an int and you're going to pass out a string, this is going to crash. So that's the same idea.
That won't compile.
It won't compile, and over here, it will run. At some point, you'll get a runtime error, or you won't get the results that you don't want. There's definitely the point that we gain on all the compiled languages are more on type safety or those stuff. But on private, public, I don't really see the benefit on that end.
Well, that will also be compile time errors as opposed to runtime errors. What you're saying is like the Python, you see the benefits outweighing the benefits of using other languages that are more object-oriented native.
Regarding object-oriented, I don't see the benefit on the other languages. Regarding the language itself, there's always, all those languages, once they're compiled, they'll be quicker to run. They have type safety as in some stuff which we could check by compile time. Python is just a runtime language. You can only catch the error if and when we encounter that error. We could have code we believe works, but just never crashed, and that had a wrong element in it and a wrong type, and we never knew about it.
Got it. Thank you.
Like a simple thing, just to show a bit of Python as well. Plenty of times I'll have, let's say, a method or something which will have a field be created onto a dictionary, and we'll have A is 42, and then something B is let's say 12, just for sake. And then I would just want to change it and say field is equal to dictionary, and then I'll go and make field A equals, what did I do? Equals 42, and then I'll just do the same piece of code for that line over there. The issue being is since I forgot this comma over here, I don't know, but field A is not getting assigned an integer. It's getting assigned an implicit tuple, which the first element is 42. This code could run forever until you pass that piece of code which requires an integer, and it'll fail, and you won't even know where it worked. I had it plenty of times, and I just had to start making sure that my linter will start warning me about disallow trailing comma tuple. See, this was a bug which I just had. And this is something which you can't get on a runtime language. You just need to have hope that you know how to read your code and everything.
Who's up for being the last question?
Last question, yes. Is the idea behind the getters and setters that it just like kind of intercepts the equals and runs a function, those properties, those decorators?
Yeah, those decorators in Python, we use decorators to get the stuff, that code, and just these sugars to, as we said, in reality, just the sugars to different class, which is a property class, and it has the getter and the object that we're getting on, and it goes into that, and it finds whatever value and it runs the code. It's not even stored on the class. It's stored outside of the class on its own object. But that's discussion on Python's internals. But the idea is just these sugars, the equal sign, as in instead of having to call a function and pass in a value to the function, I could use the equal sign, and the runtime or the compiler will just change the code to something else.
Mm.
Just like the classes in C++ as well, 100% will be, when you call, will go like stack push. If you know those double colons from plenty of languages which use those for static methods, and it passes on the instance as the first element. This is whenever C++ compiles this call, it will compile it to this.
Thanks.
All right. Thank you to Yanky Hoffman.